Magnetism is probably one of the most interesting aspects of physics, in my opinion. I mean, I can still remember some of the intrigue that I had when I was a kid with magnets and how they stuck to metallic surfaces, and just never really understood how they worked, and I still don't really understand how they work, but I think I've got a better understanding of the basic principles involved at this moment in time, which is why I'm making the video, but I still don't get how they specifically work. There's a lot of mechanics, there's a lot of physics involved, which is pretty much beyond the scope of this series, so I'm not going to go too much in depth, but magnetism is really interesting as a topic, and we're going to look at that hopefully in this video, if not another part of the video perhaps. Okay, so magnetism. Well, magnetism, essentially what magnetism is if we have a block of metal, okay, within the metal you have electrons, you have protons, but for magnetism we're usually concerned with electrons. And now electrons, they have a property known as spin, and spin lends another property called angular momentum to these electrons. And angular momentum subsequently gives rise to a thing called a magnetic moment. Okay, magnetic moments are like little bar magnets, and usually in a magnetic material like a ferromagnet, for example iron, all these magnetic moments of the electrons will be in random directions. They won't have any orientation to them. But as soon as you apply an external magnetic field that acts, for example, if we make this end the north and this end the south by applying an external magnetic field, what you'll then find is that those all those different sorry, one second. All those different magnetic fields will then start to align. They'll start to align in the direction of the north to south. So they'll all start to align. They'll all go straight up like this towards the North Pole. In fact, you also have some anti-parallel, some pointing to the south, but that's a very excited energy state, and it's actually used in MRI, the anti-parallel state, but we won't go into that in this video. Essentially what you then get is you get it aligned in that field, and after a while a ferromagnet will actually retain that particular structure, and it will remain magnetic for a while unless you bang it on a surface, etc., to de-align those magnetic dipoles. So in essence, that's what magnetism is. Magnetic materials cause these fields of magnetic lines, they're known as flux lines, to occur. Flux lines flow from the north to the south. You can kind of think of it like current, for example, in the same way that current flows from positive to negative. Magnetic circuits go from north to south. Very similar principles. So yeah, that's what a bar magnet principally looks like. So let's discuss certain aspects of magnetism in terms of formulas that we might need to encounter. So already what we discussed was that in a bar magnet, you'll have a south end, you'll have a north end, and you'll have those flux lines moving from north to south, in this fashion. And some will take a really long time and some will go really far, etc., etc., etc. And these field lines are known as flux lines. Okay, flux lines. And pretty much what flux lines are lines, or pretty much force lines. Force lines. The direction of the flux lines, of course, show the direction of the force that's going to be experienced by a particle. Yeah. Flux, in terms of a specified area, is measured. Actually, let's not talk about that for a second. Let's just okay. So, for example, let's say in a cross-sectional area, okay, in a square of 1 by 1 by 1 by 1, okay, 1 meter by 1 meter, you have flux lines 1, 2, 3, 4, 5, 6. You have 6 flux lines going into the paper. By the way, if you see crosses, it means that the field line is going through. So in essence, what you have is a cross section over here, and you have the field lines going through that thing, and you'll get arrows. Think of it like an arrowhead. And if it's coming out, you'll see dots of the paper, dots on the cross section. So anyway, so we have 6 flux lines going into this area. So in essence, the total flux in the area is 6, and the unit that we use for measurement is Webers. 6 Webers. In fact, Webers are actually very large units of flux, and usually you'll tend to deal with 10 to the minus 3, 10 to the minus 4 Webers. But yeah, so that's what flux is. It's just the number of field lines that are passing through in an area. Another quantity that you might want to know of is flux density. Flux density is equal to flux in Webers over the area in meters squared. In this case, the area is 1 meter squared. So the flux and the flux density would be the same. Flux density, the symbol that we give for flux density is B. The symbol that we give for flux is phi. And area, of course, is A. And you can have an equation, therefore. You can have an equation like this. BA is equal to phi. Another unit of measure, based on this, we know that the unit of measure is Webers per meter squared, right? For flux density. But a more common way of representing it is a Tesla. Flux density is also a measure of the magnetic strength, field strength. So the strength of the magnet is measured in Tesla, or Webers per meter squared. Right? Okay, that's something that we needed to cover. We can now discuss other types of magnets and stuff. So far we've discussed the bar magnet, but you can also get magnets formed when you have a coil of wire with a current passing through it. So here we have a coil of wire, okay, and a coil of wire is called a solenoid. It's a solenoid, okay, and we're going to pass current through. If you know the right hand rule, you'll know that the current basically goes clockwise, where your right hand thumb points in the direction of the current. So in this case, there'll be a magnetic field induced by the current in this direction. And of course, if we look at it on the opposite side, you'll find that it goes that way, that direction. Okay? And when you actually get to the solenoid itself, what you can do is you can try and wrap your arms around, or wrap your hand around the direction of the coils, and you'll find that you can see that a sort of a bar magnet figure is formed. So in this case, if you, for example, you can do it coil by coil. So I'm actually doing it coil by coil now. You'll find that it kind of comes out, what do you call it? The field lines kind of come out. So which side is it? It's going this way, so the field line should come out like this. This, and then you'll get a bar magnet forming right here, and it should go out like this. I'm just thinking about it 1 second. God damn, this is annoying. How the... Yeah, I think it's through this way. Might be through the other way, I'm not sure. But essentially what you do is the right hand rule. I mean, if it was a better... Let me draw another solenoid. This is probably not the best solenoid to draw. Let's draw this sort of a solenoid, okay? kind of top view, you can see it's slightly better. Okay. You run your hands along how the coil goes, so the coil is spinning in this direction, right? And because the coil is spinning in direction, if you put your fingers along those coils, you'll see that your thumb actually points in the direction of the magnetic field. So this will be north and this will be south, and you get a bar magnet formed, kind of like this. And that's using the right hand rule. Okay? And this is very important to realize that currents can induce magnetic fields. And this principle is important in things like transformers and electromagnetic machines, which we'll come on to in a second. So far we've come across one equation, which is sorry, that's not what we've come across, my bad. We've come across BA is equal to phi, right? Alright, now I'm going to introduce you to another equation. I'm going to write it down, and we'll discuss what it means. So phi is equal to times n times I. Now, based on that solenoid I drew earlier, which I'm going to draw again, you can have an equation that governs it. Okay? This, of course, is flux. So this is the number of field lines induced. Number of flux lines, okay? Induced. And that's determined by the number of coils, or number of turns on the coil, the current that's passed through the coil, and also this property known as permeance. And that involves the sort of material that the field lines pass through. I will discuss. Let's discuss this right now. Okay, one second. Let me delete this layer so we have more space to work with. 1 second. Okay. So, whoops, sorry. 1 second. There we go. So, okay. What I mean by permeance is, if we have a solenoid, right? Its field lines tend to pass through air most of the time, and air is actually not a very permeant material because of the fact that it's not ferromagnetic. There are not many magnetic dipoles or free electrons present. However, if we add a coil in the midst of it, so let's have an electromagnet or an iron core, electromagnetic core, I don't know what that is, and we then wrap a solenoid around that, right, and pass a current through the solenoid, we'll then have a much stronger magnetic field that's induced, and the number of flux lines that are passing through that solenoid will be increased by a lot. That's because the permeance of the iron core, in this case we'll call it the iron core, is very high. Now what permeance is, if we want to write an equation for permeance is very similar to a quantity that you might have come across in electrical physics, which is known as conductance. Now, permeance pretty much has the same equations. You have the area of the core, cross-sectional area of core. You have the length of the core, and you have this thing called the permeability, which is just a measure of how permeable the material is. Permeability. Now, if we want a high permeance, of course we want high permeability, and we want a high cross-sectional area, but we want lower length. So the ideal transformer, or for example, if we are using a high, let's not talk about transformers for the moment. let's talk about the ideal electromagnet. If you want the best electromagnet with the largest amount of flux, you want an electromagnet that has a fat core and is very short. However, there is a problem. If you have a fat core that's very short, you'll have a problem in the sense that the number of coils that you can then have is reduced. If you have a short core, then you can't have that many coils. And if you have something that's very fat, you'll have a longer length of core, which then increases the resistivity, which is a problem as well, which is followed by that equation. The resistivity will be increased, which is not ideal. Because if you have a higher resistance, then you have a lower current, which will then decrease the flux induced. So there has to be a compromise. But that, in essence, is what the ideal transformer would have. A fat core and short. But, of course, that's not always the case. So, those are the two main equations that you need to know about for now. This video is getting really long, so I'm going to leave it at that. So those are the basics of magnetism. Or magnetism? Magnetism. And in the next video we'll talk about electromagnetic machines and how electromagnetic induction works. So I'll catch you then. Bye bye.